Hi, I'm Mr. V, and today we're talking about congruence, which is our Unit 2 of the Illustrative Mathematics, and we're in Lesson 12, which is proofs about quadrilaterals. In the next 2 days, we'll also be talking about more proofs with quadrilaterals. We've been doing proofs with triangles up to this point. And before we get started, I'd like to go through some of the homework problems, and we'll start with this one. Which of the following criteria always proves triangles are congruent? Select all that apply. And we've discussed this in class where we talked about valid shortcuts and invalid shortcuts. And if you didn't know these, you should write these down, okay? Invalid, ones that don't work or don't always work. The ones that always work, the ones that we've proved in class, are the side triangle congruence theorem. And I'm going to expect you to write this out, either write it out fully or just use these abbreviations. We also use the angle side angle triangle congruence theorem and the side angle side triangle congruence theorem. What we didn't talk about, but it is still valid, is the angle side triangle congruence theorem. If you know two angles of one triangle are congruent to another triangle, then you know that the third angle as well. And here we would have the side that is not included, so you know that the third, this is actually just a version of this one, and it is valid. There are two that are not valid, at least not valid all the time. One of those is the angle shortcut, and that's because you could have one triangle that's really small. All three angles here are the same as on a separate triangle. That's a larger version of it. This is a dilation, and this is what we'll talk about in similarity in our next unit. So this is not a valid shortcut to proving triangles are congruent. And the other one is the SSA, and sometimes that works. So SSA sometimes works, but it does not guarantee it always works. So we called it the sometimes. And what are the criteria for making this work? They used to call this the HL for the hypotenuse leg because it works with if you have a right triangle. It also works if you have an obtuse triangle as being your angle that is given. So if this is the side that's given and this is the side that's given, this is the angle. Or if this is the angle and the side, this would work as well. If it is an acute triangle, the only time that it will work is if my side that is not adjacent is longer. So if this one is longer, this would work, and it would guarantee it, but it does not always guarantee it. And it doesn't always guarantee it because if the second side is shorter than this first one, I could do it like this or like this. So this would give me two different versions. It's ambiguous. Another way of looking at it is if I have an isosceles triangle, the two angles are congruent. Here I have an angle side, and if I draw the third side slanty-wise, you see this third side is shorter than the opposite angle. And so these two triangles are not congruent. So the ones that work, no, not the angles, yes, the sides. Corresponding side angle side, yes. Side, no. This works sometimes, but not always. And corresponding side angle, yes, this always works. Next question. We have a kite. We were told that this is 94 degrees, and this angle here, ZWX, is equal to 112 degrees. And we're asked to find this angle here, ZYX. And to do this, I went through a process, and I'm going to do it now for you, of explaining why these two triangles are congruent and why that's necessary to use in order to solve for this. I did not ask you to prove it. You could have just written the numbers and solved it, but I want to show you my thinking as I do this. So the first thing I want to do is to show that these two triangles are congruent. We know that two sides of one triangle are congruent to two sides of another triangle. So I have side, but there is no side shortcut. I need a third side. So I'm going to mark this side as congruent to itself. Why can I say that YW is equal to YW? And that is because of the reflexive property. And the reflexive property is one of these that I expect you to remember. We've talked about it so many times. Property. The angle is congruent to itself. A side is congruent to itself. That's the reason. And this is the side. So I could put a little S here next to this. This is going to be my side. And so I can use a shortcut to prove that the triangles are congruent. Now that I've got the side, 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 I can use the side, side, side triangle congruence theorem as my rule to say that triangle WXY is congruent to triangle WZY. And I'm not going to show that all their corresponding parts are congruent before I show that the two triangles are congruent. I'm going to use a shortcut. The shortcut I'm using is the side, side, side. So, but now that I know that they are congruent, now I can show that all of the remaining parts are congruent because the corresponding parts of congruent triangles are congruent. So I could say angle W is equal to angle Z is equal to angle X. The measures are equal. So this has to be 94. Oh my gosh, that's important. I could also say I'm going to call this angle 1 and this one angle 2. I could say that angle 1 is congruent to angle 2. Why? What rule allows me to say that? Say that their measures are equal. Well, it's the corresponding parts of congruent triangles are congruent. They're congruent, and so these have to be the same. And since they are equal, so I could, and they add up to 112, and I could substitute this in. 2 of these, angle 1 is equal to 112. So this angle has to be 56. I'll mark it in blue. This is 56, and this one is 94. Now, what rule, if I'm going to call this guy angle 3, what rule allows me to say that 94 plus 56 plus angle 3, the measure of angle 3, is equal to 180? What rule? Because you have to have a rule anytime you make a statement. This is the addition property or substitution because I'm substituting it in. So here we have the triangle angle sum theorem. This says that the angles of a triangle sum to 180 degrees. And from this I can solve so that the measure of angle 3 is equal to 30. Now all I asked you to do in this problem was to find this angle. But if I'd asked you to explain it, you'd have to go through a proof like this one. And let's see if I have any more questions down here. Okay, 6. I'm not going to go through number 6 or number 7, but I'd like you to make sure that you know and understand how to do these, okay? Instead, we're going to look at today's lesson. I can critique a proof about quadrilaterals. I can prove theorems about quadrilaterals. I can write or rewrite a conjecture so it's specific enough to prove. Let's look in your Google Classroom for just a moment. Under today's date, I put in 2 files. One is from term 1 and one is from term 2. And this is a reference table that's filled out already. And this is in light gray because this is from Unit 1. In Unit 1, we proved the triangle angle sum theorem. We proved it, and so now we're using it today in one of our problems. We also proved a number of theorems about parallel lines, such as when a transversal crosses parallel lines, or if lines are parallel, then a transversal crosses it to form congruent corresponding angles, like these. I said it in the form of a song to help you remember. A transversal crosses parallel lines to form congruent corresponding angles. And its converse is true as well. The converse is not starting with the parallel lines, it's starting with corresponding angles. If corresponding angles are congruent, then the lines have to be parallel. The lines that it crosses have to be parallel. Well, looking down here, there are some other theorems. And if you want to know a list of the theorems that we've seen, go to your reference table. That's what it's there for. Print it out. If you don't have a printer, copy it by hand. That's what I would normally have you do, is copy it by hand and then show you the results afterward. So here you have, if 2 figures are congruent, then the corresponding parts of those figures must be congruent. So the corresponding parts of congruent figures are congruent. So if these are congruent, starting with this part, then all 3 sides must be congruent, all 3 corresponding angles must be congruent. And you have to say the word corresponding, because if you didn't know it, I could have 5 parts of one triangle that are congruent to 5 of the 6 parts of a second triangle and them not be congruent. That's why we use the word corresponding. And if you don't believe it, well, you try it on your own, and maybe sometime I'll show you how to do it. Now, the converse of this is also true. If all the pairs of corresponding parts are congruent, then the triangles are congruent. Fortunately for us, we don't have to prove all of the 6 measurable parts, the 3 angles and the 3 sides of one triangle are congruent to another in order to prove they are congruent. We can use a shortcut. And we've done this by using our segment theorem. If they're the same measure, then they're the same length. If they're the same length, then they're congruent, which means that the one can be mapped onto the other with a finite set of rigid transformations. And then we've used that for transferring and for proving our triangle theorems, such as the side angle side triangle congruence theorem. Now we're going to use these shortcuts, the side, angle, side angle, the side, and these other ones. And we're going to use them in proof like this right here. Notice, after I have enough information to show the 2 triangles are congruent, I'll use the shortcut. And after I use the shortcut, I'll use the corresponding parts are congruent so that I can talk about the other parts. We've also done the isosceles theorem. Some of you may recognize it as the Pons isonorm. If I have an isosceles triangle, then the base angles are congruent. Its converse is also true. If the base angles of a triangle are congruent, then it is an isosceles triangle. Here we have a parallelogram. A parallelogram, by definition, is a quadrilateral with both pair of opposite sides are parallel. And so we've proved that both pair of opposite sides of a parallelogram must be congruent. We've also proved that opposite angles must be congruent from this thing. The perpendicular bisector theorem says that if a point is equidistant from 2 endpoints of a segment, then it is on the perpendicular bisector. And I like the converse of it, which says if a point is on the perpendicular bisector of a segment, then it is equidistant from the 2 endpoints of the segment. These are all ones that we've proved. Definition of a rectangle is an equilateral quadrilateral or a quadrilateral with 4 right angles. The definition of a rhombus is a quadrilateral with 4 congruent sides. And if a parallelogram has at least 1 right angle, it is a rectangle. This is one that we are going to prove today. So these are found in your Google Classroom in this section. I left a chart for you to download. You're going to answer these questions: which ones are true, which ones are false. Some people tried to say, I should anonymize this, that all rectangles are squares. That's not true. I can draw a rectangle that is not a square by just making it longer on 2 sides than on the opposite sides. And the adjacent sides. So rectangles are always parallelograms. Parallelograms aren't always rectangles, but they can be made into a rectangle is a parallelogram. All squares, they have right angles, don't they? And so that's what the definition of a rectangle is that the squares have 4 right angles. So all squares are rectangles, but not necessarily all rectangles are squares. If you put neither of these, that would be incorrect. So next we went to a GeoGebra. So I'm going to also make sure that this is found in your reference table. In our GeoGebra assignment, which I'm going to demonstrate for you here, we have pretenders. These are square pretenders. And your task was to determine, number 1, which figures can be dragged to make a rectangle, which figures are rectangles, always, which figures are always parallelograms, which ones can be dragged to make a parallelogram. And the only way to do this is to test all of the vertices. You do a drag test. And when you do a drag test, does it stay a rectangle? Yes, it does. Does it stay with a B? B cannot move. C, yes, it does. D, yes, it does. And if I do, and it looks like I can move this in a weird way. F looks like it's going to be a square. G does not move. H still makes it a square. And E does not move. J. Oh, this is a parallelogram. This is not always a rectangle, but it can be made to a rectangle. I think. Is it always a parallelogram? Well, I move K, L, yes. I, yes. Oh, this is interesting, isn't it? Always a parallelogram. Here we have a square, If I move this point, it stays a square. If I move this point, it becomes a rhombus. How about this one? Still stays a rhombus, and this one does not move. Here I've got this one does not move. You have to check all of the vertices. Now, why do you do that? Well, here if I'm going to check on Z makes it a rectangle. It's a parallelogram. Is it always a parallelogram? I don't know. It looks like it could be. It's going to be a square. It could make it into a rectangle. I can make it into a rectangle. I can move V. I can't move V. When I move W, if you didn't change it, this does not always have to be a rectangle or a parallelogram. It could be a trapezoid. And it could be a bow tie, which is not a polygon. When it crosses like this, it is not a polygon. So going back to our lesson here. From conjecture to proof. Here's a conjecture. Now, this is where I demonstrate for the next 3 pages. I demonstrated this. All rectangles are parallelograms is the conjecture. To write this as a proof, first of all, what do we know about rectangles? We know they have 4 right angles. What do we want to prove? We want to prove that it's a parallelogram, which means we want to prove that both pair of opposite sides are parallel. We can rewrite the conjecture to identify what is given and what is proven. So given angle A, angle B, angle C, and angle D are right angles, because it's a rectangle. Prove AB is parallel to DC, AD is parallel to BC. We're going to prove that both pair of opposite sides are parallel. Now, I could have said, given that this is a rectangle, prove that it is a parallelogram. But I'm being more specific so that we can actually mark the drawing and so we can actually take something from this and make it a statement that we can use. So I'm going to mark the drawing with 4 right angles, because this is one thing that I can mark on this for sure. In the next few pages, I would have you explore and come up with and decide on what we know about rectangles and how we do this. I'm going to just draw it here. I know about parallel lines. I want to prove that they are parallel. This is a straight angle. Since this is 90 degrees, this has to be 90 degrees. Oh, looky. These are alternate interior angles formed by this transversal crossing these lines. That means that these 2 lines must be parallel by the converse alternate interior angles theorem. I'll say it again. Here, if I extend this line, this makes a straight angle. These 2 angles have to add to 180. Since this is 90, this has to be 90. Oh, looky. This angle and this one are alternate interior angles, and they are congruent, meaning this transversal crosses lines that must be parallel by the converse alternate interior angles theorem. The alternate interior angles theorem says if the lines are parallel, then the alternate interior angles are congruent. The converse says if the alternate interior angles are congruent, then the lines are parallel. And since I've shown that both pair of opposite sides are parallel, I've proved that this is a parallelogram. I've proved that all rectangles are parallelograms. And now we go to page 9. Here are some conjectures, the first one that I wrote. Then there are 4 more, and this one should say E, and it will on the corrected version. And you're supposed to pick one of these. You can use technology to explore it. You can rewrite the conjecture in the form of a given with the given information, and the proof, which is what it is you're trying to prove. Draw a figure, mark the diagram, and mark any information that you can remember for sure. Remember, you have to have a rule if you're going to mark any extra information. And then you're going to write a rough draft. And I'm going to do this now for each of these to show you what you could be doing. You try it on your own, and you can check yourself with my work if you want. And I suggest you do. So the first one, let me see if I can go down and do this. I think I've got to go down. So the first one, if a parallelogram has at least one right angle, then it is a rectangle. I'm going to say this as a given and then statement. So I'm going to say given quadrilateral ABCD. And I'm going to write down what does it mean to have it be a parallelogram. Well, that means that AB is parallel. This is the symbol for parallel to CD. We could say that BC is parallel to AD. And it says that you have one right angle. So I'm going to say the measure of angle A equals 90. And we're going to prove that it's a rectangle. So to prove it is a rectangle, I really have to prove that the measure of angle A is equal to the measure of angle B, which is equal to the measure of angle C, which is equal to the measure of angle D, which is equal to 90. That's what I have to prove. I'll draw this and I'll mark my drawing with what is given. So here's a drawing. If I can select my pen tool. Here's a drawing. I have A, B, C, D, B. And I'm given that this side is parallel to this side. It's a parallelogram. This side is parallel to this side. And I'm given that this is 90 degrees. To prove that all four angles of a parallelogram are 90 degrees, I'm going to draw, well, let's see, if this is a parallelogram, I will extend this side, and I'm going to draw alternate interior angles. Because the alternate interior angles theorem says a transversal crosses parallel lines to form congruent corresponding angles. If lines are parallel, then alternate interior angles are congruent. Since this is a straight angle, and these two angles have to add up to 180, this has to be 90. I'll use that same argument over here at this side and say this. Also, earlier we proved that opposite angles in a parallelogram are congruent. All four angles are 90 degrees, therefore this is a rectangle. That's my rough draft. I did not write it out, but you get the idea by me talking about it. If you want to write it out, that's great. So here we have a quadrilateral. So given ABCD, and it has two pair of opposite sides that are congruent. So I'm going to say AB is equal to CD, and those are opposite sides. And I could say BC is equal to AD. That is, the measure of segment BC is equal to the measure of segment AD. Prove that it's a parallelogram. It's a parallelogram. What that means is that AB is parallel to CD and BC is parallel to AD. Now, previously, we proved that if it's a parallelogram, that the opposite side, both pair of opposite sides are congruent. This is the converse of that. We have not proved this, so you cannot just assume it to be so. If I have my figure A, B, C, D, I'm going to mark what is given. These two sides are the same. These two sides are the same. What I need to prove is that these two sides are parallel and these two sides are parallel. I'm going to do that using triangles. I'll draw an auxiliary line here. And I know that this is congruent to itself. I'm going to say it out loud. You would write this down by the reflexive property. These two triangles, ABC, CDA, are congruent. Why? Because of the side, triangle congruence theorem. And then I can say that this angle, which we'll call angle 1, is congruent to this angle, angle 2. Why? Because the corresponding parts of congruent triangles are congruent. And these are alternate interior angles formed by these two lines. And they're congruent, so by the converse alternate interior angles congruent, these two lines must be parallel. I will use that same argument for this angle, angle 3 and angle 4. These are congruent because of the corresponding parts of congruent triangles are congruent. Since they are congruent, that means, and they are alternate interior angles to these two lines. Notice I'm not talking about this angle. We're talking about this one and this one. That means that these two sides must be parallel. Both pair of opposite sides are parallel. Therefore, this is a parallelogram. Part D. If the diagonals of a quadrilateral both bisect each other, then the quadrilateral is a parallelogram. So we're going to be given, I'll type this in. Given ABCD, so my parallelogram is my quadrilateral. I'm going to say AC intersects BD at M such that AM is equal to CM and BM is equal to DM. What that means is they bisect each other. AC, when it intersects, is going to cut this into two equal parts, and BD, when it intersects, CD is going to cut this into two equal parts. So we're going to prove ABCD is a parallelogram which means that AB is parallel to CD and BC, comma, BC is parallel to AD. So let's draw a picture of this and get a better insight as to how we're going to solve it. I will not write it out, but I will draw it and talk about it, and you can write it if you desire to write down all of the steps. So here we have a quadrilateral. We'll label it A, B, C, D. Notice I go in clockwise order. I do not go zigzag. If you zigzag, you're not making a quadrilateral. You're making a zigzag, a bow tie. So here we have the diagonals. This is congruent to this. And this one is congruent to this one. It does not say it's a rectangle. Looks kind of like a rectangle. That doesn't mean it's squat. But here we have two sides. Oh, looky. We also have this pair of angles that are congruent. Why? Because they're a vertical pair. Vertical angles are congruent. Similarly, these two angles are congruent. So triangle, and this is M, point M in the middle. Triangle AMB is congruent to triangle CMD. Why? Because of the side-angle-side triangle congruence theorem. This means that I could say that this angle, we'll call it angle 1, is congruent to this angle, this angle, which we'll call angle 2. Alternate interior angles that are congruent form parallel lines. These are parallel. In the same way, here I have angle, side, angle, angle, side, angle. Remember, these are congruent because they're vertical pair. And this was given that these are the same, these are the same. So by the side, angle, side, triangle AMD is congruent to triangle CMB. Now I have this angle and this one are congruent because of the corresponding parts of congruent triangles are congruent. I'll call this angle 3, and this one angle 4. And now, since these alternate interior angles are congruent, by the converse alternate interior angles theorem, these two sides must be parallel. This is a parallelogram. And I think that's it. I don't know. Did I do all of them? No, I think there's one more that I didn't do. Here we go. The diagonals of the quadrilateral both bisect each other, and they are both perpendicular. Then the quadrilateral is a rhombus. So I'm going to say, write this as a given. This is a long lesson. If you want to skip ahead, you can. But if you want to watch and listen to this, how this is done. So I'm given, and what are we given? We're given quadrilateral ABCD. And we're given that AB, AC, and BD intersect at M. Such that AC is perpendicular to M. I'm going to use the perpendicular signal in just a minute. BD is perpendicular to it. And AM is equal to CM. BM is equal to DM. Prove that ABCD is a rhombus. What does it mean to prove it's a rhombus? That means that AB is equal to BC, is equal to CD, is equal to AD. That's all four sides are congruent. That's what it is we're going to prove. And I need to use the perpendicular symbol. I need to write it in pen, so I'll use this right here, perpendicular. Now, let's draw a picture of this. I'll draw it kind of like a rhombus, even though I don't know that it's a rhombus yet. I have A, B, C, D. These diagonals bisect each other at right angles, so these are all four right angles. We also know that these bisect each other, so this is congruent to this one, and this one is congruent to this one. What I need to prove is that all four of these sides are congruent. And here we have the side angle side, side angle side. These two triangles are congruent. So triangle DMA is congruent to triangle BMA because of the side angle side, which means that the corresponding parts are congruent, so these two sides are congruent to each other. Now, if I can do the same thing here, and I can because I have the side angle side, side angle side, so triangle AMB is congruent to triangle CMB by the side angle side triangle congruence theorem. Because the corresponding parts of congruent triangles are congruent, CPCTC, AB has to be congruent to BC. And by corollary, you can also say that this is congruent. So therefore, you have the proof. And this is what you were supposed to prove one of and do it. Wrote your rough draft, and then we checked it. And we could check it with each other and look at for more. There is more here. If you want to do some more experimentation, you can. But the synthesis of this activity, the synthesis is, while all of those conjectures are true, only one of them is what we're going to use later on. If a parallelogram has at least one right angle, it must be a rectangle. And this should find way into your reference chart. So here is the lesson synthesis, and this is where it gets interesting. So the idea is to focus your attention on the work needed to go from general to specific. A conjecture. All rhombuses are parallelograms. We just proved that the thing about the diagonals of if they're perpendicular and they bisect each other, then it's a rhombus. Here we're going to prove that all rhombuses are parallelograms. And these are three statements that students made, and they're incomplete. They're not quite there yet. And so let's look at their statements. Andre said if ABCD is a rhombus, then it is a parallelogram. Well, he needs to have a given, and he needs to have a prove statement. And he needs to say more than it is a rhombus. He needs to, using the definition of a rhombus, he needs to tell me that AB is equal to CD is equal to BD is equal to, AB plus B is equal to BC is equal to CD is equal to AD. All the four sides are congruent. And if that's true, then to be a parallelogram, AB has to be parallel to CD and BC has to be parallel to AD. So it doesn't give us enough specific information to figure out what it is we're going to prove. Bob says if AB is equal to BC is equal to CD is equal to DA, so he's showing that it's a rhombus, then AB is equal to CD. What's your critique for him? Well, to be a parallelogram, both pair of opposite sides have to be parallel, and he only gives us one. So that's a critique. Now, Claire, oh my gosh, ABCD has four congruent sides, then the opposite sides are congruent, so it must be a parallelogram. Well, let's critique hers. First of all, we know that parallelograms have opposite sides congruent, but we don't know if all opposite shapes with opposite sides congruent have to be parallelograms. So proving this wouldn't prove that the shape was definitely a parallelogram. We knew from the theorem that we proved before that if we started with a parallelogram, that the opposite sides are congruent. But to prove the converse, I think Bob has the right idea starting it off here. He needs to prove that both pair of opposite sides are parallel. And for cool down, you can write this proof. You can explain how she can use this fact. And golly, that's a long